in course.
Yes. Sure, it's from school. I think we're good. 2 minutes. It takes some time for you to start thinking.
I think I can close it.
I want to close it.
So that sometimes someone block your view.
That's still the same file.
The time.
That's still the same file.
Good morning, class. Good morning. You're welcome to another round of Chemistry 101 class. We will continue with electrochemistry. But before we go on, I asked you a question yesterday, but I didn't get any response. I asked if any one of you has gotten the lecture note for electrolytic cell. If you are hearing me and you're already in class, can you please respond? I want to know if you already have your first lecture note with you. We are still on the second lecture, as you can see on your screen. I want to know if any one of you has already lecture note. Good morning. The hero had 478. Good morning. Okay, someone responded. He said he hasn't got the lecture notes. You will need to see your class rep. The lecture note had been sent to your class reps, to your various class reps. You need to see your class rep, or you see me in my office today. I can also make you a class rep, and you can also assist in the dissemination of the any other person who has gotten a note. That is very important. I need to know. There's nobody has said he has gotten it. Lydia Agumbiade, you're welcome. Do you have your first lecture note with you? Anyone with his or her first lecture note? Then it means the class reps are not doing the job. It means they are not representing you. All of them have the notes with them. I expect them to have sent it out by now. So everyone is saying no. So you might need to see me in my office today for the note. You might need to see me in my office today for the note. Jeremiah David, Everyone is saying no. Note for first lecture, no one here has gotten it. Okay, you can check me at White House Chemistry Department, room 216E. Room 216E. Room 216E. All right. I just need a few representation, maybe about 10 people. Maybe about 10 people from across all the departments. So we can continue with our lecture for today. So we can continue with our lecture for today. So yesterday we were trying to make us understand how to determine the EMF of an electrochemical cell. And if you recall, I gave you an expression for this, and this is that expression. But to make it even more clearer, because some of you may be wondering, okay, E reduce minus E oxidation, or yes, or where oxidation is taking place, the anode in which oxidation is taking place, and then the anode in which reduction is taking place. You can also take your forward minus your cathode. You know that that is where your reduction reaction will take place. And you can identify your anode. You also know that that is where your oxidation is taking place. So I asked you to provide the E cell, the standard EMF for this particular cell yesterday. Is there anyone here who has been able to do that? I have given the address to my office. I said White House Department of Chemistry, second floor, room 216E. E for Emmanuel. Okay, 216E. I only need like 10 people to represent others, and these 10 people will, will be the ones to distribute the notes to everyone. So is there anyone in the class who has been able to provide solution to that question? If you have, can you kindly let us know your answer? All right. So there is a fundamental problem with that particular question. But the way the question is posed, can we approach it exactly the way it is posed? All right. Let us approach the question exactly the way it is posed. Now, going to the question. Okay, electrode and hydrogen electrode are connected. Definitely, there is going to be a potential difference across the two electrodes. Electron will flow, current will also flow. So what is the EMF of the cell? We have been given the reduction potential. Look at the direction in which this electrode is written. It is from the ion to the neutral atom. That is reduction. So what the value we are given here is a reduction potential. And looking at the other one as well, it is from the ion to the neutral hydrogen, molecule. So ion to neutral molecule or atom is telling us that this is also a reduction potential. Okay, so that is the standard. Conventionally, electrochemical series table, or what we know as activity series, we provide the potentials as reduction potentials. They will provide the potential as reduction potential. I want you to take note of that. So all you only need to do from the values provided is to identify which of the electrodes is now your cathode and which one is your anode. So once you're able to identify your cathode and your anode, you just use this expression and you determine the EMF of the cell. Okay, so usually, the lower potential, is the anode. Okay, is the anode. If you go back to the previous example, all right, you will see that in this example, hydrogen has the lower potential, okay, and it is what? It is the anode, okay? Hydrogen has the lower potential, so it is what? The anode. And if you come here as well, you realize that the zinc electrode also has the lower potential. So it is what? It is the anode. Similarly, there is not going to be an exception to this. This is also going to be the anode. The hydrogen with the lower potential is also going to be the anode. So having identified our anode, so that means the nickel electrode is going to be our cathode. So the EMF of the cell, the standard EMF of the cell is going to be E cathode minus E anode. So we have identified our what? Our electrode. So the E cathode there is the nickel, okay? The nickel electrode, 0.25 is the value, okay? The standard reduction potential for the cathode, as given here, is 0.25, okay? Minus 0, okay? That gives us plus 0.25 volt. So this is a wrong solution. So that's why I said there is something fundamentally wrong with the solution provided in the note. So I want you to take note of that. So this is going to be the EMF of the cell. Because if an EMF gives you a negative, if the EMF of a cell is negative, okay, what does that say about the cell? It means the cell is not, is not going to operate in a forward direction. It's not going to operate in a forward direction, okay? Or may not even, because what you are saying is that your delta G, okay, your delta G is not going to be negative. We are going to get to that. Your delta G is not going to be negative. So that is the implication of having an EMF of negative, okay? So the EMF of the cell is going to be plus 0.25 volts. And we can go on. But before we do that, let me give you the first attendance code. The first attendance code. The first attendance code is S6. TEES6. That is the first attendance code. Okay. So we have treated this yesterday, so we can go on to the next slide to start the concentration effect, which will lead us to the Nernst equation. We are going to come about the next equation very soon. The thermodynamic standard free energy change, which is delta G naught, is related to the standard EMF of a cell by equation 19. Okay, so the E naught here is the EMF of the cell. All right, F is the Faraday constant, and N that you have here is the number of electrons involved in the cell reaction. Okay, for a reversible cell reaction at equilibrium, equation 20 is employed. Okay, if you have a cell reaction that is an equilibrium process, okay, you can employ this equation where you have forward and backward reaction. You know, the electrochemical process is such, go forward or backward depending on the condition of the reaction, and it can also attain equilibrium. I believe you have done chemical equilibrium, so you understand what we mean by equilibrium constant. So in this expression, which is delta G naught equals minus RT ln K, natural logarithm K. The R there is called the gas constant. The gas constant is given as 8.314 joules per mole per Kelvin. Okay, it's a constant. All right. The T is the temperature of the reaction or the condition, the atmosphere. Okay, and K is the equilibrium constant. So because we have the thermodynamics standard free energy to be equals to equation 20, we can relate equation 19 and equation 20. So if we relate equation 19 and equation 20, we get equation 21. And from that equation 21, we can also determine the EMF of the cell of the a cell that is occurring at a reversible process. Under a reversible process, we can obtain the EMF of the cell, provided we know each of these parameters, provided we know the temperature, okay, and then we know the equilibrium constant. All right, and we also know the number of electrons that are involved in the electrochemical process. Any problem up to this point? Do you have any problem up to this point? No. Okay. Now, at the standard conditions of 1 atmosphere, unit activity of electrolyte, and 25 degrees Celsius. You know, this is not the same as STP, all right? This is just the standard condition under experiment, all right? That is experimentally approved to be the ideal condition for this process. Okay, 1 atmosphere, unit activity, and then room temperature, which is about 25 degrees Celsius, especially in this part of the world. Okay, now under these various conditions, okay, you know that the temperature is going to be 298 Kelvin, all right? 298 Kelvin, that is, you convert 25 to Kelvin plus 273. So that will give you 298 Kelvin, all right? And then the only thing that you do not know here is the number of what? The number of electrons that are involved, which will depend on the type of electrochemical process that is occurring. R there is a constant, which is this. T is also going to be a constant generally under this standard condition. Okay, so it's going to be 298, and Faraday is also a constant. Okay, so if you convert this equation to natural logarithm in base 10, log to base 10, if you convert this equation to logarithm in base 10, okay, you are going to have this, and then you substitute each of these values. You substitute your R, you substitute your temperature, and then you substitute your Faraday, which is 96,500 coulomb, okay, you are going to have, ordinarily converting that will be RT over F, okay, R2. Let me clear the screen. So converting this will be E cell for such an electrochemical process is going to be 2.303 RT, okay, over NF log to base 10. Okay, that is what you have here. And when you substitute your value of R, which is the gas constant, you also substitute the temperature, which is 298 Kelvin, and you substitute your Faraday constant, you end up with this value 0.059 over N log K to base 10. This is log to base 10. So, but do we have any implication converting from natural logarithm to log to base 10? No, there's no implication. You can as well use this directly as long as you are so cautious and you know that you are using natural logarithm. Your answer is not going to be different from when you convert it to log to base 10. Okay, and we are just trying to provide a general formula when you have already considered the temperature, the Faraday constant, and also the gas constant. So you have this general formula as well. Okay, so that is the expression. So now let us look at this example. We have the reduction potentials. The reduction potentials of the electrodes of the cell iron slash iron 2 slash slash gold 3 slash gold are, so we have been given the reduction potential, all right, and then the reduction potential for gold as well. So these are the two electrodes. You have this electrode and then you have this electrode. Okay, this is the cell, this is the cell, all right. So write the half cell and the full cell reaction, half cell and the full cell reactions, and state the polarity of the cell, all right. So if we are to write the half cell reaction, let us take this electrode, all right. First, you need to identify, okay, before you can write that, you need to identify which of the electrodes is likely going to be your cathode and which is going to be your anode. If you look at the reduction potential given here, you see that the lower value is iron 2. So it means that iron is going to be the one that will undergo oxidation to produce the electron. Okay, this is the, but this is not completely the half cell, but this is the first thing you start with because you have been able to identify your anode. So this is going to be your anode. Okay, but before you put that it is going to be your anode, let us write for the cathode. So which of the electrode will take up the electrons produced? Definitely is going to be the gold electrode. So the gold electrode will take up the electron that is released by what? By ion. So 3 electrons will take this, 3 electrons will take, go 3 to what? Gold atom. So 3 electrons will take it. So this is not going to be a balanced equation. So what that means is that you are going to multiply this by 2 and you will multiply this by 3. Okay, so in the end, you are going to have 3 Fe, okay, giving 3 Fe2 plus 6 electrons. Plus 6 electrons. So you do the same. Here you are going to have 2 gold 3 plus 6 electrons to 2 gold atom. 2 gold atom. So this is your anode. Okay, this is going to be your anode, and this is going to be your cathode. So the question says, write the half cell. So the first half cell is this, the one of ion, 3Fe going to 3Fe2 plus 6 electrons. The second half cell is for gold, 2 gold 3 plus 6 electrons giving 2 gold atom. So we have attended to this first question. What is the full cell reaction? Now, the full cell reaction will be to add the 2 half reactions together. So when you add the 2 half reactions together, you are going to have 3Fe plus 2 gold 3 giving because the 6 electron is on the left hand side for the gold and it is on the right hand side for the ion, so they will cancel out when you add them together. Okay, they will cancel out. So you then end up having 3Fe2 plus 2 gold atom. So the number of electrons that is involved in this process is 6. Okay, as you can see, the number of electrons involved in this process is 6. Now, state the polarity of the cell. Of course, we have already stated that the anode is the ion electrode. The cathode is the gold electrode. So that is that about the first question. Calculate the cell potential. So we then come back to our popular expression. The standard, EMF of the cell is going to be, assuming this process occur under standard condition. So the cell potential is going to be E cathode minus E anode. So since we know our cathode to be the gold electrode, so the value there is 1.520 volts minus 0.440. So in the end, the EMF of the cell is going to be the EMF of the cell is going to be 1.520 plus 0.440. When you add this together, you have 1.960 volts plus 1.960 volts. That is the cell potential. What is the free energy change? So the delta G, remember, okay, is going to be 0.059 over n log k. All right, that is one expression. Okay, but which expression do you think is more appropriate? You also have delta G equals minus n f e cell. Okay, so this is more appropriate because you already have all the parameters that you need to calculate the free energy change in this second expression. You know the number of electrons involved. You know that the Faraday constant is 96,500 column, and you know the E cell, which you already have here. So if you plug in these values, you are going to get your free energy change. Then the equilibrium constant. The question is also asking us to calculate the equilibrium constant. Remember that since you already have your delta G, okay, you can substitute your delta G from here into this place, and then you will obtain your equilibrium constant. So predict the feasibility of the cell reaction. The feasibility is asking you to determine whether the reaction is going to occur or it will not occur. The feasibility. Will the reaction occur or it won't occur? If delta G is negative, the reaction will occur and it's going to be spontaneous. Okay? The fact that you also obtain your E cell to be positive is also an indication that the reaction will proceed in the forward reaction. In the forward direction. The reaction will proceed in the forward direction. All right? That means the reaction will occur. Your E cell being positive and your delta G being negative is a pointer to the fact that the reaction will occur. Okay? And it's going to be spontaneous. So if your E cell is negative, what that means is that your delta G is going to be positive. And the implication when you have a positive delta G is that the reaction is going to be non-spontaneous. Non-spontaneous. Also, your value of K is also an indication of whether the reaction will proceed and will proceed well. Okay? If your K is very large, so let us look at the value of K that is obtained in this in the solution to this problem. Look at the value of K, very large value. So the K value, the E cell value, and delta G values are all indicators to whether an electrochemical reaction will occur or not. And each of these parameters, each of these indicators have shown that this particular electrochemical reaction will proceed in the forward direction. The K is large, okay, which means product, concentration is going to be far greater than the reactant, okay. The E cell, which is positive, is also telling us that the reaction is going to be spontaneous. Similarly, delta G, which is negative, the reaction is going to be spontaneous. So this is the value of the delta G obtained from the question, the solution to the question. And here is an expression used. You can use this, and you can as well substitute your value of delta G to obtain your K from the expression I gave earlier. So E cell is positive, delta G is negative, and K is high. Each of these parameters is an indicator that gives the direction of change. For this example, each parameter shows the cell reaction to be spontaneous to the far right of the reaction. I want to get a feedback on this. I want to get a feedback on what we have done so far. Okay? Are you okay up to this point? Up to this point, are you okay? Jeremiah David, I didn't get your question. What do you mean by I? Sir, please, if I is low, will the reaction proceed backwards? What is I in all of this? Do you mean to write K? Owosheni Ayodeji, how do we know the value of delta G? It means you have not been following. Okay, now take the second attendance code. The second attendance code is 38 S8Y. S8Y. S for Sunday, or S for sodium. That is the second attendance code. So if the electrolyte departs from the standard state of unity, or the concentration of the electrolyte is less or greater than 1 mole per dm cube, then the actual half cell potentials must be calculated from the Nernst equation. This is where the Nernst equation is applicable. You remember that when you have an electrode, let us say this is an electrode, okay, and you have the electrolyte. This is an electrode. You cannot have a complete cell. What you are going to have here is a half cell, all right? You will only have a complete cell when you connect it to another half cell or another electrode, okay? All right? So this is what will now produce current. This is what will produce current. This is electrode A, this is electrode B, all right? So now let us assume that electrode B is our standard hydrogen electrode. Our standard hydrogen electrode operating under, because of the word standard, it means it's operating under the standard condition. 1 atmosphere pressure, 1 mole per dm cube concentration of the electrolyte, okay, and the temperature is 25 degrees Celsius. Let us assume that this electrode B is the standard hydrogen electrode, and the value of the reduction potential for this electrode B, which is our standard hydrogen electrode, is what? 0.0 volts. All right. So when we connect electrode A to the standard hydrogen electrode, automatically the value we are able to read from here, from the voltmeter here, is going to be the reduction potential, the standard reduction potential of electrode A, okay? The standard electrode potential of electrode A. We are able to read from the voltmeter connected to here, provided that the concentration of the solution in electrode A is also 1 mole per dm cube, 1 molar, which is 1 mole per dm cube, capital M this time around, 1 mole per dm cube, and the temperature is 25 degrees Celsius. Okay, so we are going to read out a value that is equal to the standard reduction potential of electrode A, which is going to be here. All right. No, the question now is, what if the electrode is operating under a non-standard condition? That is, the concentration is not 1 mole per dm cube. It is either greater or less than 1 mole per dm cube. How do we determine the standard reduction potential? That is the question. Okay, we can no longer connect it to the standard hydrogen electrode and read out the value from the voltmeter. We can no longer do that because the electrode is not operating under standard condition. One of the conditions is not met, which is the concentration. The concentration is either greater or less than 1 mole per dm cube. How do we then determine the electrode potential, which we can call reduction potential of that electrode? That is where the Nernst equation is important. That is where the Nernst equation is important. So we continue to elaborate on this. The Nernst equation arose from experimental measurements the result of which show the linear relationship between the cell voltage and the electrolyte concentration. The next equation is given by equation 23. Okay, so there has been an experiment. Okay, an experiment proved that the cell EMF, okay, is related to the concentration of the electrolyte, directly related to the concentration. The cell voltage is directly related to the concentration of the electrolyte, which means that electrolyte with a different concentration, with a concentration that is higher than 1 or less than 1 mole, okay, the EMF it's going to produce is directly related to the concentration of that electrolyte, where Q is the reaction quotient of the half cell. You know, the electrode now is a half cell, so we are interested in the half cell, which is the electrode. Okay, the one electrode is a half cell. Okay, now what do we mean by reaction quotient? Let us take, for example, this electrode. Okay, the electrode to what? The electrode to reduce, I mean, this electrode contains iron 3 as electrolyte. Okay, iron electrode, iron 3 as electrolyte, which will take up one electron and it will become iron 2, okay, on the surface of the electrode. Okay, so for example, the reaction quotient is going to be the concentration. This is concentration of the product, which is iron 2, over concentration of the reactant. All right, so that is the reaction quotient. Okay, so the EMF of the half cell, of this particular half cell, we are taking this as an example. So of this particular half cell, which we are taking as an example, is going to be equal to E naught minus RT. You know, we define the next equation in number 23 initially. So we have it here. It is still the same equation that we are expanding here using a specific example. So the half cell, the EMF of the half cell is going to be E naught minus RT over NF, ln the concentration of iron 2 over concentration of iron 3, which is the reaction quotient that we have already defined here. Okay, you can rewrite this expression and then this will change to positive. It will change sign to plus. That is, the denominator here become the numerator here, and the numerator here become the denominator. Okay, that is very simple for all of you to understand. Okay, where E naught is the standard electrode potential if the electrode were to be operating under standard conditions. Okay, so you know, before now we have not defined E naught. This is now the definition of E naught. What is E naught again? If, let us assume that this is the electrode. Now it is not operating under, let us assume that this is the electrode. Now it is not operating under standard condition, and that is why we are using this Nernst equation, all right, to determine the, you know, the EMF of the half cell. And the EMF of the half cell, if you must know, is going to be equal to the, you know, electropotential of the half cell. If you must know, the EMF of the half cell is going to be equal to the electropotential of the half cell. Okay, so now that is why we are using the Nernst equation. Now, what is the electropotential of that half cell if it was to be operating under standard condition? That is E naught. Okay, and that is available in physical chemistry textbooks. Okay, so the standard reduction potential of this half reaction is available. Okay, take note of the word standard now. The standard that I put there now indicate that if the half cell were, you know, if the reaction, the half reaction or half cell reaction were to be operating under standard condition, so the electrode potential becomes standard electrode potential, and that is available in the literature. Okay, so that value is going to be a constant which is available in the literature. So the one that we want to know now from the Nernst equation, the electrode potential of the half cell when it is operating under non-standard condition will be given by the Nernst equation. Okay, so this is available in the literature, and then the concentration of the participant, which is ion 3 and ion 2, when known, and then the number of electrons that are involved, the values of RT and F. When plugged, then we can obtain the electrode potential of the half cell of an electrode that is not operating under standard condition, or the electrode potential of a half cell that is not operating under standard condition. If it were to be under standard condition, all we just need to do is to connect it to what? Standard hydrogen electrode, and we measure the value on the, or we measure the reading from the voltmeter connected. Okay, so at 298 Kelvin, the electrode potential is going to be this value. Okay, you can convert this equation, which is natural logarithm here, you can convert it to log to base 10. You have this. At 298 Kelvin, you substitute the value of R. R is 8.314 joules per mole per Kelvin. Okay, the only thing that you can get is the N, because we are trying to write a general expression, not now, okay, a general expression. But for this time, we are still specifying the concentration of the participant, the reactant, and the product. Okay. Now, generally, if you look at this expression, you see that the oxidized form of the participant is the numerator. The concentration of the oxidized form over the reduced form, all right, of the participant. This is a general expression. So if you really do not know which one will be the numerator, which one will be the denominator, just look at the form of the species in the half cell. What is the form of the species in the half cell? Is the species in its oxidized form, or is it in its reduced form? So once you are able to recognize that, you know that the oxidized form with this equation, you know that the oxidized form is going to be the numerator, and the reduced form is going to be the denominator. So for this electrode, okay, the voltage is going to be, now using this expression, particularly this general expression, all right, using this general expression, what will be the electrode potential for this electrode? Okay, all right, so the oxidized form, okay, is the reactant, all right, the reactant, and the reduced form is the product. Okay, you can calculate the oxidation state of manganese here. Okay, and the oxidation state of manganese on the product side is 2, manganese 2, but here it is manganese 7. So a species with a higher oxidation state is oxidized. Okay, lower oxidation state is reduced. So the reduced form is the denominator, and the oxidized form is what? The numerator. So these are the species that will determine the dynamics of the reaction. The manganese 7, okay, tetraoxomanganese 7, and also the hydrogen ion, okay, the hydrogen ion concentration. So impute this, and then you will be able to determine the electrode potential of this half cell. So the Nernst equation, so this is Nernst equation. When anybody asks you for Nernst equation, okay, all you just have to write is that the electrode potential of an electrode, okay, that is operating under non-standard condition is given by E equals to E naught, which is the value of the electrode potential where the electrode if the electrode is assumed to be operating under standard condition. Okay, so E naught is the value for the electrode if it were to be operating under standard condition, plus RT over NF ln concentration of oxidized form over concentration of reduced form of the species that is contained in the half cell. Okay, this is Nernst equation. So the Nernst equation can also be used. And remember, you can also write this equation in this form: E naught minus RT over NF ln, it then become reduced form over oxidized form. This is just mathematics. Okay, so once you put minus here, you know that the reduced form will be up and then the oxidized form will be the denominator. So the next equation can also, another application of the next equation, it can also be used to calculate the cell voltage at non-standard condition. So now you are not talking about a half cell, you are talking about a complete cell. Okay, I want you to get this clearly. Let me give you the third attendance code. The third attendance code is FR44Z. FR44Z. That is the third attendance code. So I want you to get this clearly. Now we are talking about another application of the Nernst equation. You are not talking, in this case, you are not talking about a half cell. Okay, you want to determine the electropotential of a half cell. We are saying that you can also use the Nernst equation to determine the EMF of a cell. Now we are talking about EMF. We are talking about a cell. Okay, the EMF of a cell, that is, you now have a complete cell. You have both the anode, okay, and the cathode connected together. We have a complete cell, not a half cell, not one of these two. We have two half cells. Okay, but if the complete cell, which is the two half cell, if the complete cell is not operating under a standard condition, you know, if it were to be operating under a standard condition, you can use the formula E cell equals E cathode minus E anode to determine the EMF of the cell. Okay, very simple. Okay, but what if the cell is not operating under a standard condition, under the standard condition? What if the cell is not operating under the standard condition? And that is what we are saying. You can use the Nernst equation to determine the EMF of the cell. It then becomes the EMF of the cell. You are not going to put naught here because it's not going to be standard EMF again, because the condition of operation is not standard. All right, so it's just going to be E cell, okay, equals to the standard EMF if the cell were to be operating under what? Under standard condition. The standard EMF of the cell, if the cell were to be operating under standard condition, minus 0.059 over n log concentration of the species A over species B. Okay, species A over species B. This is just an expression that talks about log to base 10. okay, log to base 10. You can also write this expression in natural logarithm. It will give you the same, but generally, if you are writing it in natural logarithm, is going to be minus RT over NF ln K. You know, you can just call it ln K, all right? Or ln concentration of species A over concentration of species B. That is the Nernst equation to determine the EMF of a cell that is not operating under the standard condition. Okay, where the E naught cell that you have here is the EMF of the cell if it were to be operating under standard condition. So now let us look at this example. The Nernst equation can also be used The Nernst equation can also be used to calculate, I have 7 minutes more, to calculate the cell voltage at the non-standard conditions. For example, the cell reaction zinc plus iron 2 giving zinc 2 plus iron generates E naught at 0.32. That E naught there, the naught, this naught that is there, is actually referring to the fact that this is going to be the EMF value at standard condition. All right. So E naught equals 0.32 volts at 25 degrees Celsius. That is at standard condition. Okay. This cell will produce this amount of EMF at standard condition. So the Nernst equation for the cell that is operating at non-standard condition, none, not no, at non-standard condition is going to be E cell equals 0.32 minus 0.059, because we already know that for this cell to operate, 2 electrons will be involved. 2 electrons will be involved. So it's going to be over 2 log to base 10 concentration of the product over that of the reactant. That is what will form this concentration of the product over that of the reactant. Note that the concentration of zinc and that of iron are constant or are non-active species. This I need not overflow because I believe you have gone through that during your chemical equilibria lecture. Okay, so note that the concentration of zinc atom and iron atom are constant or are non-active species and are justifiably by the law of mass action not included. Okay, not included in the calculation of the standard, in the calculation of the EMF of the cell, all right, or the equilibrium constant. Okay. So the reactant and product concentration, okay, that is electrolyte and its product, do affect the cell voltage. That is, the concentration of the reactant and product do affect the cell voltage. And that will lead us to what we refer to as concentration effect. Concentration effect on the EMF. So if concentration, okay, increased, all right, the product concentration increased, what will happen to the voltage, all right? So all of this is illustrated with these examples. All of this is illustrated with this example using this last example as the cell. Okay, what will happen if we increase the concentration of the product and allow the concentration of the reactant to be constant and vice versa? So that is illustrated here. All right. And because we have seen from this illustration that concentration affects the value of the EMF, all right, then we will explain this principle using a particular cell as an example. Okay, this is the principle on which the functioning of the concentration cell is based. So there are some cells that are referred to as concentration cell because concentration of reactant and product affect the EMF value of the cell. Okay, so scientists developed a cell that is operating only based on difference in concentration of the electrolyte solution. Okay, now you have the same electrode, electrode A, connected to each other, electrode A. But because of the difference in the concentration of the electrolyte, current will still flow in the external circuit of the cell. This type of cell is called the concentration cell. So there is an example, a specific example, and that is this. The cell Ag/Ag plus with the concentration 0.001 molar slash Ag plus with the concentration 0.1 molar. You see that this one is more concentrated than this one. The one I ticked is more concentrated than the third one. Okay, so this cell is a concentration cell. It's called a concentration cell. The anode is the more dilute electrode, while the cathode will be the more concentrated electrode. The EMF, the standard EMF of the cell is going to be 0 because the electrode is the same, the same electrode. So the standard EMF of the cell is going to be 0. The standard EMF of the cell is going to be 0 because each of them will have the same reduction potential. So you have E cell equal to E cathode minus E anode. But the E cathode is the same as E anode. Therefore, the EMF, the standard EMF of the cell is going to be 0. Okay, so that is that about the concentration. Even though the standard EMF of the cell is 0, the current will still flow in the cell, and this is how it's going to occur. So the standard EMF of the cell is 0 because the standard reduction potential E naught of both electrodes are equal. All right, so the more dilute solution is the anode. Okay, is the anode. That is why it is releasing the electron, while the more concentrated solution is the cathode, and that is why it is what? It is taking up the electron. So when you put this together, okay, you will see that the more concentrated solution becomes what? Becomes the reactant, while the more dilute electrolyte becomes the product. Okay, so the E cell of the cell can be determined using the Nernst equation, which will be 0.00. This is the value of the EMF, the standard EMF of the cell, minus 0.059 over 1. The number of electrons that is involved in this reaction is 1. Log of the concentration of the reactant over concentration, the concentration of the product over concentration of the reactant. And then you have this value of EMF, 0.118 volts. So in spite of the fact that the standard EMF is 0, that cell is still able to produce an EMF of 0.118 volts because of the differential in the concentration of the electrolyte. So we end the lecture on electrochemical cell today. Tomorrow we will start another lecture, which will be cells and battery. And then after that, we'll start a new topic entirely, and that will be radioactivity. Before I leave, I would like to have a feedback about what we have done so far. Is there any problem with any area of the lecture? Let me know. Any question? So remember, I will need about 10 people to come to my office today to get the lecture notes for the first lecture on electrolytic cell and the second lecture, which we have just concluded today. I've given my address. My office address is 216E. Okay, thank you, Jeremiah David. So in the absence of question, which is an indication that you all understand the concept, then this is where I'm going to draw the curtain on electrochemical cell. We'll meet again tomorrow at 8 o'clock a.m. to start a new, not entirely new topic, but an extension of electrochemical cells, which is going to be on cells, the difference between cells and batteries. And that will be the topic that will round up the whole electrochemistry, which we started sometimes last week. So do have a beautiful day. Thank you.
ẹ̀ǹdẹ̀ o ṣé méjèèjì ló ní duplication ní àdéhùn níbẹ̀ èwo ló ní duplication bẹ́ẹ̀. The same question all over. Mo ní ṣe 203 ní àbí 27? Okay, àgbà mi 207 ní ṣe wá fún mi ní wàhálà ẹ̀jẹ̀ sáré ṣe. Ṣèbí 11 ní 207 àbí wà lẹ́sẹ̀ bẹ̀rẹ̀? Okay.